All right, let's get started. Let's see. Okay, so in the past few lectures, we have looked into the MOSFET as a device. We have looked into different treatments of the MOSFET. So, for example, we have looked into the energy band treatment, and we have also looked into the different equations of the MOSFET. That what is the equation of the MOSFET in the linear region or the triad region? Also, what is the equation of the MOSFET when it is in the active region or the saturation region? So today we'll be looking into more details of the MOSFET, that using these equations, how you can solve circuits. So that's what we are going to learn starting today's lecture. But till now, what we have learned is that what is the MOSFET as a device and how you can sort of derive the equations that we'll be using from this class onwards. So that's why as a background, it was very important to understand how the MOSFET device behaves, how the ID versus VDS equations or ID versus VGS equations look like for the MOSFET. But once we have an idea about the equations, it's probably easier to use those equations in an actual circuit. And that's what we'll be learning in the next few lectures. So since this is a circuit-related class, so whatever we are discussing from today's lecture would be more important in terms of the homeworks or in terms of the exams. Okay. So this handout is already posted in your Canvas. And of course, this is the 3D view that you have already looked into, that, okay, you'll have the gate, you'll have the source, and you'll have the drain. These are the three primary terminals of the MOSFET. And of course, this is the bulk or the body terminal, which is connected to the bulk of the device. So this is the source region of the device. This is the drain region of the device. This here is the channel where the length L is indicated. That is the length of the channel. This is the width of the channel. So eventually, when you are designing a particular circuit, you'll be asked to find out what is the W over L ratio, or what is the aspect ratio of the MOSFET. So that's basically what is meant by designing a circuit using MOSFETs, that you eventually need to find out what is the W over L ratio, okay, or the aspect ratio of the device. Now, just go over this text, which we have already discussed in the class multiple times. The symbols, again, something that we have discussed in the class again. So N-channel MOSFET, there could be many different symbols that you'll find in books. And all of these different symbols will represent the same thing. So we'll primarily be using this symbol in the class. And that is if you look into most books or even publications, this is the most predominant symbol that you'll be seeing that represents N-channel MOSFETs. There is also another symbol that you'll be seeing in digital logic books that looks like this. So these are primarily the two most common symbols for N-channel MOSFETs, but there are other symbols as well. For example, in your LT Spice, you'll see that N-channel MOSFET looks like this. But eventually, I probably recommend that in all your calculations or in your exams, you'll most likely find a symbol that will look like that. And why I will prefer this symbol? Because it represents the direction of the current through the device at the source terminal. So this is the direction of the arrow, and that is the direction where the current flows from the drain to the source for the N-channel MOSFET or the N MOSFET, right? Because for N MOSFET, the carriers are the electrons. So electrons will flow from source to drain, current will flow from drain to source. So your current will be an outgoing quantity from at the source terminal. So that's why I prefer this symbol. In digital logic books, you'll also see this symbol being predominantly used, so that's also fine. But if you're using this without any kind of arrow, which means you might get a little confused about where is the drain, where is the source, and that's why I'll prefer this symbol more over the last one. Okay. All right. Now, the regions of operations, again, something that we have already discussed, but this is just a summary that, okay, when is the MOSFET device on? The MOSFET device is on when your gate to source voltage VGS is more than a certain threshold voltage. So if your VGS is greater than or equal to VT, or sometimes you'll see this represented as VTH, that's the threshold. So your VGS, if your VGS is greater than or equal to the threshold voltage, then the MOSFET device is on for an N-channel MOSFET. For a P-channel MOSFET, we'll see how that equation is slightly change, but in most cases, you'll see that there is a direct correlation between the equations for the N-channel MOSFET and the P-channel MOSFET. So for now, we'll only concentrate on the N-channel MOSFET and look at all the equations of the N-channel MOSFET. For the P-channel MOSFET, I'll tell you how to sort of find out the correct equations from the N-channel MOSFET equation. So for now, don't worry about the P-channel device. For the N-channel MOSFET, this is what your equation should look like when the device is on. And again, VGS has to be more than VTH. Remember, if you remember about the energy barrier, that okay, you're at your source side, this is source, this is drain, and in between you have the channel. So you want an electron to flow from the source to the drain, right? And it has to cross this energy barrier. So what is the easiest way to make sure that the electron can cross the energy barrier? Reduce the height of the barrier. And that's something you can do by applying a positive voltage. That's something we have discussed multiple times in the previous few lectures. So that's the understanding about your gate to source voltage or your threshold voltage that you should have by now. And what this says is that as the gate to source voltage becomes higher than the threshold voltage, the device can turn on, which means that the electron can cross this energy barrier, which will now be reduced. So let's say the energy barrier will look something like that. And in that case, it will be easier for the electrons to pass from the source region to the drain region. So VGS has to be more than VT. That's the equation for the device to be on. For triode region or linear region of operation, of course, the device has to be on. If the device is off, you cannot have a triode region. In fact, like when you go to graduate class, you'll see that there is a sub-threshold region as well, that when this VGS minus VT or VGS greater than VT, if this condition is not satisfied, it is said that the device is in sub-threshold region because you are below the threshold. Even in that case, you can have a small amount of current flow. Some of the electrons can have enough energy that they can pass from the source region to the drain region, even if the barrier is high. So that is called the sub-threshold operation. We'll not discuss a lot of sub-threshold operation in this class, but if you take a graduate level class, analog IC1 or analog IC2, you'll see that we'll discuss more about the sub-threshold region, because in that region, the currents are lower, so you can get really, really low power operation. And what does low power mean? That your phone's battery can probably stay for a month instead of just operating for a day. Right? So it is possible that eventually with sub-threshold operation, as the device properties are becoming better and better, and we are getting to know about more and more low power circuits, eventually someday will come when your phone's battery will last for a week instead of lasting a day. Okay. So that's why the sub-threshold region is also very important. But right now in this class, we'll not discuss that because that is more advanced electronic circuits. Right now, we'll assume that the FET is always on, which means that your VGS is more than VT. And as your VGS is more than VT, you can have two different regions of operation. One is called the triode region or the linear region, where your VDS is less than equal to VGS minus VT. And again, this is something we discussed in previous class, that why VDS has to be less than VGS minus VT for triode region, and why VDS has to be greater than VGS minus VT for the active region or the saturation region. Remember this diagram, that if this is your source, this is your drain, and this is how the channel looks like. The pinch-off condition will be when your this channel looks exactly like a triangle, and the end point of this triangle or this particular vertex of this triangle lies exactly at the drain terminal. So at that point, your VDS is equal to VGS minus VT, because VGS minus VT is the voltage. If you did not apply a VDS at this point, if you did not apply a drain voltage, the voltage at this point would have been VGS minus VT, because VGS is the voltage that you're applying at the gate. There will be a drop, a threshold voltage drop, because unless you have the threshold voltage applied at the gate, there will be no formation of electrons in the channel. Right? Because you are, by applying that gate voltage, what you're doing is that you're attracting electrons from the bulk region or attracting electrons from the source and drain region, and then eventually you're forming the channel. But to form the channel or to make sure that the energy barrier is reduced by a significant amount, your VGS has to be more than VT. So that can be considered as a VT amount of drop, or the threshold voltage amount of drop that you'll see in the channel. So in the channel, you'll actually have a voltage of VGS minus VT if you're not applying any drain voltage. But as soon as you apply a drain voltage, some of those electrons will be attracted back towards the drain. Why? Because again, the drain terminal is positive. Electrons are negatively charged. Some of those electrons will get attracted back at the drain terminal, and that's why you eventually see this triangular kind of shape of the channel. The channel does not remain rectangular, it becomes triangular. And that's because these electrons which are near to the drain region get attracted toward the drain, which is positively charged. At the point when VDS is exactly equal to that VGS minus VT, you will have zero voltage at this point because of the gate, you would have had a voltage of VGS minus VT, but because of the drain voltage, you are attracting all those electrons back to the drain terminal if you are applying a voltage of VDS, which is exactly equal to that VGS minus VT. So you sort of compensate for that VGS minus VT voltage at the drain side, which makes the thickness of the channel at this point equal to 0. So that's your boundary condition. That's the condition when you start pinching off the channel. If VDS is more than that, your pinch off point will move towards left. Okay. If VDS is less than that, you'll not have any kind of pinch off. So that's the boundary of your triode region and saturation region. So at triode region, for triode region, your VDS is less than VGS minus VT. For saturation region, your VDS is more than VGS minus VT. Okay. And as you remember, that VGS minus VT is also called the overdrive, because that's the voltage by which, the amount by which you are applying a gate voltage which is higher than your threshold voltage. That's your overdrive. It's similar to you overclocking your laptop, right? So there is if you're running really complex processes, or let's say if you're playing a high definition game in your laptop, you'll see that the laptop will overclock. They will run at a higher frequency. So this is similar to that concept that you're overdriving your gate by an amount which is higher than the threshold voltage. So the transistor can already turn on, but you are applying more gate voltage so that you can eventually get higher amount of current through the device. And that will be evident when you look at the equations of triode and saturation regions. Again, these are some things that I'm just repeating. We have already discussed these things in the previous lecture, but I'm just repeating this so that you remember better. Okay. So the definition of the regions, once again, cutoff region or subthreshold region, that is when your VGS is less than VT. So then no channel will exist, and ideally no current can flow. But we'll see in graduate classes that there is still a small amount of current flow in below the threshold region, and that is the region why instead of calling cutoff, in graduate classes you'll call it the subthreshold region. And that is the correct way to represent it. There's no cutoff. It's not true that there is no current flow. For now, you can sort of assume that, okay, there is no current flow because the amount of current is probably nanoamperes or picoamperes. But that amount of current could also be useful in certain applications. So that will be called the subthreshold region of operation or cutoff region of operation. But in this class, we'll not discuss that in detail. What we'll discuss in detail is the region when the transistor is on, when it is not in cutoff, which means that VGS has to be more than the threshold voltage. And if VGS is more than the threshold voltage, you'll have two different regions of operation. One could be the triode or linear region, one could be the active or saturation region. And again, we have proved these equations in the last class that in triode region, your ID will be equal to mu times COX times W over L multiplied with VGS minus VT, that's your overdrive, multiplied with VDS minus half VDS squared. So that's your equation for triode region. In your saturation region, the equation is much more simpler. It's half mu COX times W over L times VGS minus VT whole squared. And that is true because remember that this is the equation of this is the region of your triode, right? This is where your device is in triode. So till this point, it is following this equation. Now, at the maximum point, again, if you go back to the previous lecture, you'll see that this point occurs when your VDS is equal to your VGS minus VT. When you reach that pinch off point, the exact boundary condition, you'll reach at this maximum point when your VDS is equal to VGS minus VT. Now, if you put your VDS equal to VGS minus VT in this equation for the triode, you'll see that you'll eventually end up with the equation of saturation. Okay. So you just put your VDS equal to VGS minus VT. So you have a VGS minus VT over here. You multiply that with another VGS minus VT. So you get VGS minus VT whole squared. And this is half of VGS minus VT whole squared. So you're getting the full VGS minus VT whole squared minus half of the same VGS minus VT whole squared. So inside these square brackets, you'll have half of VGS minus VT whole squared. This half is coming towards this left-hand side. That's the same half that we just discussed now. And within the square brackets, you just had VGS minus VT whole squared. So that's the same equation. Assuming that, okay, at this maximum point, you're starting with this saturation region. Questions? For the lab, which question are you referring to? Because, yeah, for the lab, there could be a linear region, there could be a saturation region. I'm not sure which exact question you're referring to, but yeah, of course. So when you're analyzing the triad portion, you will follow this equation. So your current will be a function of drain to source voltage. As you're increasing the drain to source voltage, if your current keeps on increasing, then you are in the linear or the triad region. If it does not increase anymore, or if it increases by a very, very small amount, then you are already in the saturation region. Okay. So in your lab, as you carry out this experiment that you increase your VDS from a small value to a larger value, you'll actually be able to see this curve. More questions? The small amplitude signal. Yeah, are you asking about the small signal analysis that when we actually look at the gain? Okay, that's a great question. We haven't come to that in this particular class yet, but this is how the ID versus VDS looks like. We haven't yet talked about the AC small signal yet. Now your AC small signal could be, let's say this is just how the device behaves as you're applying a particular amount of VDS to the drain and source terminal, and you're trying to look at how much current is flowing. Right? It does not need to be AC. At this point, even if you apply a DC voltage here, you'll see a DC amount of current flowing through the device. Okay, so this is just a DC analysis of the device. So what DC analysis of the device says that, okay, as you are increasing the drain to source voltage, you'll see your drain current behaving in this manner. Now, you can fix any of those voltages as your operating voltage. That you'll say that, okay, I want to fix my drain voltage at this, my source voltage at this, which means that, let's say I'm operating at a particular VDS. Let's say I'm here. Now, around this point, if you apply a AC signal at the let's say at the gate terminal, you'll eventually see, or let's say if there is a, we'll come to that, but right now what I'm going to say is that the AC operation could be around this point, or it could be around this point as well. So right now we are not talking about AC operation at all, the small signal operation at all. What we are saying is that if you apply a particular amount of drain to source voltage, what is the amount of current that you're expected to see? And this will be true even if you are applying a DC voltage. Let's say you apply a DC 1 volt, you'll see some DC current through the device. You apply a DC 3 volt, you'll see some amount of current through the device. You apply a DC 4 volts, you'll see the current through the device is almost the same, which means it has reached the saturation region. So this will be true even in terms of DC. Because we haven't, in this particular equation, or when we derive the equation, we did not distinguish the fact that whether we are applying a AC voltage or an AC current. It's just that you apply a voltage, you get a current, just like you can do it across a resistance. Okay. But I'll come to your question like toward the end of today's class. Okay. All right, few other things that are very important, that even though we mentioned that in the saturation region, your current is almost constant, you'll see that it's not exactly constant. It will still keep on increasing a little bit with respect to VDS. And why that is so, again, something that we had discussed in the previous lecture, that if you look at the exact form of the saturation equation, in the exact form of the saturation equation, this will not be W over L, Rather, it will be W over L prime, where L prime is the effective length of the channel as you have pinched it off. So as you're pinching off the channel, your effective length keeps on reducing. And how much of that reduction will be, by how much your effective channel length will reduce, will be a function of VDS. That's why apparently, even though there is no VDS in this equation, this L prime will be a function of the of VDS, and that's the reason why the exact equation in your saturation will be looking something like this. That you can write down the first part of the same equation, that you have half mu times COX times W over L times VGS minus VT whole square. That's the equation that we had written in the previous page. But that multiplied with 1 plus lambda VDS, that will give you the exact form of the equation, which will also be dependent on VDS by a small amount. Why I'm saying that by a small amount? Because this lambda is called a channel length modulation parameter. And why is it called a channel length modulation parameter? Because again, as I said, that is this L in this form is basically L prime. And what L prime means is that as your pinch off point is moving towards left as a function of your VDS, your channel length is modulating, your channel length is changing. And to represent that scenario, that okay, your channel length is changing, you have this channel length modulation parameter in the equation. The value of the channel length parameter is usually in the range of 0.1 or 0.2 or 0.05, so it is very small. So even if you change your VDS by 1 volt, lambda times 1 volt will be only 0.1, right? So this will be 1 plus 0.1. So we'll have only a 10% increase in the current, even though you're increasing your VDS by 1 volt, something like that. Okay. So, but what will that mean is that your exact plot of ID versus VDS, that would look more like this. That will look, even in saturation, you'll have some kind of a slope. And that slope will in fact be your 1 upon output resistance. Because remember, what is resistance? Resistance is output voltage, change in output voltage divided by change in output current, right? Output resistance, if I call it RO or Rout, that is change in output voltage. So your output voltage across the MOSFET is VDS. So change in output voltage will be delta VDS divided by change in output current will be delta ID. So basically, if you take a derivative of this curve, derivative of the ID versus VDS curve, and take an inverse of this, that will be the slope of that will be the RO, which means that the slope will be 1 upon R. Right? What is the slope of this curve? That is derivative of ID with respect to VDS. That's the slope of any Y versus X curve. Right? If you have a Y-axis, if you have an X-axis, what is the slope? The slope is delta of what the change in Y-axis divided by delta change in X-axis. That's the same thing we are saying over here. It's just that because RO is voltage over current, resistance is voltage over current and not current over voltage, your slope in this case is 1 upon RO. And if you can also calculate the slope from this equation. What you need to do is that you need to take a del ID, del VDS. So you take a derivative of this ID equation with respect to VDS. That would give you your 1 upon RO. And 1 upon RO can also be represented as GO, which is basically your output transconductance. So 1 upon transconductance is your resistance, or 1 upon resistance is your transconductance or output conductance. So I should say output conductance, not transconductance, because transconductance has a different meaning and we'll come to that. So GO is your output conductance, that is 1 upon the output resistance, that is del ID, del VDS, or the derivative of ID with respect to VDS. And if you take the derivative of this equation with respect to VDS, what would you get? You will get this lambda term coming out, because this 1 will become a constant and everything else is a constant. So that term will become 0. So this lambda VDS multiplied with this entire term, you are taking a derivative of that. So your lambda will be outside, multiplied by half mu and COX W over L times VGS minus VT whole square. That would be your derivative of ID with respect to VDS, which is also equal to lambda times ID. So what was the equation for ID? Equation for ID was this term. So let me just write with a different color. So let's say this half mu COX W over L times VGS minus VT whole squared, that term is present in the ID equation as well as in the GO equation, correct? So this term is equal to ID divided by 1 plus lambda VDS, because ID divided by 1 plus lambda VDS, if you take this 1 plus lambda VDS term on the left hand side, that would become this half of mu COX W over L times VGS minus VT whole squared. So ID divided by 1 plus lambda VDS is basically your half mu COX W over L times VGS minus VT whole squared. So this entire term becomes lambda ID divided by 1 plus lambda VDS. Okay. So that's your 1 upon RO, which means RO will be equal to 1 over this entire term. So basically it would be RO would be equal to 1 plus lambda VDS divided by lambda ID. Now this is the exact form of the RO or the output resistance. But if you just assume that this lambda VDS term is very small, because your lambda is itself very small, lambda is 0.1 or 0.05, so it's very, very small. If you just ignore this term as compared to 1, because this will be 1 plus 0.05 or 1 plus 0.1, something like that. So if you just ignore this term with respect to 1, RO will be equal to almost equal to 1 over lambda I. So that is one equation that you can use in your calculations, in your homework, or in your exams, that your output resistance will be 1 over lambda ID. Okay. So next, what we are going to discuss is that as now we have some idea about the equations of triode region, equations of the active or saturation region, and the equation of, let's say, the output resistance, we'll try to take a look at a circuit which could be similar to your homework number 4 problems, and we'll try to see how to solve those kind of problems. But before going there, I would also like to mention one thing, that this term which I had encircled with this red rectangle, that is half of mu times COX times W over L times VGS minus VT whole squared. Right? You can now simplify this into different forms. So what are the different forms? You already know that mu times COX, that's called the process transconductance. So you can write this as half of K dash times W over L, but K dash is the process transconductance, W over L times VGS minus VT whole squared. Now you also know that if this is process transconductance and if this is aspect ratio W over L, then the multiplication of the process transconductance with aspect ratio gives you the device transconductance. The device transconductance is represented just as K. Again, something we had learned earlier. So this becomes half of K times VGS minus VT whole squared. Okay. You also know VGS minus VT is called overdrive. So you can just write it as half of K times V overdrive squared. So instead of writing this long equation, you can write the same thing just with this. Right? So if you want to just remember what is the formula for current in the active or saturation region, except for this 1 plus lambda VDS term, which would be mentioned in the question whether you want to consider the channel length modulation or not, that will be mentioned in the question. But if you just ignore this 1 plus lambda VDS term for a moment, this is what your equation looks like in the active region. And this is very easy to remember, right? Half of K times V over L squared, that's it. You can represent K as K dash times W over L, and then K dash again as mu times COX, and V over L as VGS minus VT whole squared, or VGS minus VT. But this is all you need to remember in terms of the equations. All right. Now, when we are trying to solve the problems in homework number 4, one thing that I'd like to mention first is that, let's say if you have a circuit that looks like this, that okay, you have a MOSFET, You have a resistance at the drain terminal. The source terminal is grounded, and you apply a voltage at the drain terminal above this resistance, right? So you're applying some kind of VDS across the MOSFET. You're applying some kind of VGS across the MOSFET. Assuming that the MOSFET is on, that the VGS is more than the threshold voltage, the equation for the MOSFET in saturation, in active region or saturation region, will be half of K times V overdrive squared. Right? This equation, half of K times V overdrive squared. So that's your equation for your current. As your VGS, if your VGS is very small, your current through the device will be very small as well. Ideally, if your VGS is less than the threshold voltage, your current through the device will be 0, because if the device is off, this equation is not even true. Ideally, there should be no current through the device when VGS is less than VT. So if you look into the right-hand side, which is the voltage transfer characteristic, and this is something we had already discussed when we were studying op-amps, and you saw that the VTC for op-amps also look like this. We are sort of circling back to the same concept and saying how, or showing how your VTC would look like this once again. So let's say your x-axis is your VGS, that's your input voltage to the MOSFET, right? The gate to source voltage is the input voltage to the MOSFET, that's your x-axis in this plot. And your y-axis is your drain to source voltage, which is the output voltage of the MOSFET. Why are you calling it the output voltage? Because the source is grounded, the input is at the gate, so that whatever voltage you have at the drain, that's your output voltage, right? And that will be equal to VDS, because the source voltage is equal to 0. So the MOSFET's output voltage in this case is equal to VDS, the input voltage is equal to VGS. Now, as you are increasing your VGS from 0 value to VT, so from 0 to VT, what is happening? As the VGS is less than VT, you do not have any current through the device ideally. If you just assume the cutoff to be true, and if you assume that, okay, there is no concept of subthreshold right now in this class. Okay, so subthreshold region means that your current through the device is equal to 0. Let's just assume that. If that is true, then there is no current flow through the device when your VGS is in between 0 and VT. If there is no current flow through this device, what would be the voltage at the drain terminal? There is no current flow through the resistance or through the device. So what would be the voltage at the drain terminal? It will be equal to VDD. So that's why you see that in this region, the output voltage is equal to VDD. Correct? The entire voltage drop is happening across the device because the device is off, and that's why the drain voltage is equal to VDD, or drain to source voltage is equal to VDD. Now, as the device turns on, as your VGS becomes more than VT, we will assume that the device will actually turn on in the saturation region or in the active region. And again, why is that? Because your VDS is very high. To start with, your VDS was equal to VDD. You are just crossing your gate to source voltage. You're making your gate to source voltage just higher than your threshold voltage. So VGS minus VT will be a very small quantity at this point, or at this point, right? VGS minus VT, or the overdrive, is very small at this point, because gate to source voltage is just higher than VT. The definition of overdrive is VGS minus VT. If your VT is 0.7 volts and if your VGS is 0.71 volts, then you are just 10 millivolt above your threshold voltage, right? So your VGS minus VT or the overdrive is very small at this point. Your VDS was already at VDD. Your VDS was very, very high. Let's say it was already 5 volts. So of course, 5 volt is much higher than 10 millivolts. Everyone will agree to that, right? If 5 volt is much higher than 10 millivolt, then at this point, the device is in saturation region, because your VDS is higher than VGS minus VT. That's the definition of your saturation region. So right after the cutoff, you start with your saturation region. Okay, as you are increasing your VGS, right after cutoff, you'll get your saturation region. And when you are in the saturation region, your current will keep on increasing as a function of VGS minus VT whole squared, correct? So as your current is increasing as a square term of VGS minus VT, you'll see a steep drop. You'll see a sudden drop in the output voltage because the current through the device keeps on increasing more and more, which means that the current through the resistance also keeps on increasing more and more. So the drop across the resistance keeps on increasing more and more. The drop across the device will keep on reducing more and more. As your current through the resistance keeps on increasing, the drop across the resistance keeps on increasing, which means the drop across the device will keep on decreasing. The total voltage can only be equal to VDD. The drop across the resistance and the drop across the device, the summation of those two voltages could only be equal to VDD. If the drop across the resistance increases, the drop across the device has to reduce. There is no other way. If the drop across the device keeps on reducing sharply, this is how the plot will look like. Okay, everyone agrees? So that's how your output voltage will look like from this cutoff point into the saturation. And because this is reducing sharply, as you see that if you increase your VGS by a very small amount, the decrease in your VDS will be a large amount. And that's the reason why you can expect gain in this region, that you change your VGS by a small amount, the change in VDS will be much, much higher. Right? And that's why you have a gain in the saturation region. Now, eventually you will reach a point as your VDS is reducing. So remember that this is your VDS, and as your VDS is reducing, eventually, and of course your VGS is increasing, eventually there will be a point when your VDS will become less than VGS minus VT. At that point, you will enter the triode region. And in triode region, you do not have that sharp increase in current as a function of VGS. Remember, what is the equation of your triode region? If you go back here, the equation for your triode region looks like this, correct? So it is not a sharp function of VGS. It's just a linear function of VGS. In the saturation region, it was a squared function of VGS. It was VGS minus VT whole squared. In this case, the squared term is not there. So in the triode region, the current will not be a sharp function of the VGS anymore. So that's why you'll see that slope will degrade, and you'll see something like that. Right? The sharp slope will not be present anymore. So that will be your triode region, and eventually your VDS will become very, very small and will be almost equal to 0. So that's why your VTC will still look very similar to what you had for the op amps. Now coming back to your question, what will happen if we apply a AC signal at the input? So how does the small signal, or why do we even have a small signal voltage gain using a MOSFET? Or why does the MOSFET work as a small signal amplifier? Imagine that you have a gate to source voltage here, which is a DC voltage, but along with that DC voltage, you're applying an AC small signal as well. So this is an AC source. That's why you'll see that VGS is represented in terms of a lowercase letter. The lowercase VGS says that this is an AC source. So you have an AC VGS and a DC VGS applied simultaneously at the gate terminal. What does that mean? That you have your gate VGS voltage, and that VGS voltage is an AC voltage around a particular DC point. So you have this particular VGS DC voltage. Let's just assume that this is the DC voltage. This is the DC VGS. This is the DC VGS you have. And around that DC VGS, you have a small signal AC. In this case, we are representing it with a triangular wave. It can also be a sine wave. It can also be a square wave, and so on. Okay. So if you have a small signal applied around that DC VGS, so this is your input voltage that you're applying, that it is changing a little bit around that DC VGS that is set by this battery or this source. Okay. If you extend this point, so this is the point on your VTC. This is the DC VGS on your VTC. What would be the DC VDS on your VTC? That would be the point on the y-axis, correct? This is the DC VDS in your VTC. But the highest and lowest point on your gate to source voltage, that will be determined by how much of a small signal you're applying, how much of the AC voltage you're applying. Now again, for some of you, this might not be clear, but when we talk about small signal, we're talking about an AC signal. Because in most of the cases, you want an amplification out of this device, which means your input is small, your output is large. That's what you want. That's the definition of amplification. Your input is small, output is large. So small signal analysis means that you're applying a small AC signal at your input, you're expecting a large AC signal at your output. And the analysis will give you that how much of an amplification should you expect based on the different properties of the device, based on the transconductance, based on the output resistance, and many other properties that we'll take a look at in the next few lectures. But right now, from this particular curve, it should be clear to you that why do you have an amplification in the first place? This is your input. The input is applied around a gate voltage of VGS, a DC gate voltage of VGS. But if you have a small signal excursion around that DC VGS, the minimum point of that excursion is corresponding to this point. Again, extend that point here. So that would be one of the extremities of your output VDS. Again, the maximum point of your input small signal is here. Extend that point. And this will be corresponding to your output VDS and one of the extreme points of your output VDS. So as you see that at your output, you have a triangular signal which looks much larger than the input triangular signal. And that is only possible if the slope of this region is steep. If the slope of this, so let's say I just take the absolute value of the slope. If the absolute value of the slope is more than 1, then only you'll see amplification. If the absolute value of the slope is less than 1, you'll not see any kind of amplification. You'll actually see attenuation. But in most cases, as you'll see, and we'll derive that, we'll prove that why the slope in the saturation region is more than 1. If the slope in the saturation region is more than 1, you'll expect this amplification to happen. And that's why the transistor in this configuration acts as an amplifier. Okay. So let me just remove this so that it is clear to you how from the small input we are getting this large output. It's just that you take these dotted lines, you move across these dotted lines, that will give you an idea about what is the VGS corresponding to the minimum value of your input and what is the corresponding output voltage value on top of this VTC. The voltage transfer characteristic gives you the value of your output voltage corresponding to any input voltage, right? It does not know whether it is a small signal, it is a large signal, whether it is an AC or a DC. It has no idea about that. It just says that if you give me this much amount of input voltage, this will be the output voltage. That's what your VTC will tell you. So you can just plot any point. It can be a triangular wave, it can be a sine wave, it can be a square wave, and the VTC will tell you what you can expect at your output side. And if the slope of your VTC is more than 1, you expect this voltage gain. Okay. Now to understand that how much voltage gain we'll have or whether the slope will be more than 1 or not. To understand that, we have to look at a very important property of the MOSFET, which is called the transconductance. The transconductance is represented as Gm. So you know that G is basically 1 upon R. R is resistance and G is conductance. G is usually represented as 1 upon R. The subscript M represents that it's a mutual transconductance between the input and the output. So if you have an input voltage, the gate to source voltage is your input voltage and your drain current is your output current. So it's a transfer quantity between your input and your output. That's why it's called a transconductance. So GM is small signal ID divided by small signal VGS, or you can also represent it as del ID over del VGS. So you just have to take a derivative of your ID versus VGS equation with respect to VGS. So remember in the previous scenario, when we were finding out the output resistance, we took a derivative of your ID with respect to VDS because all you wanted was the output quantities. Now you want a transfer quantity. you know that your output is a current, but you want to know what is the relation of that output current with respect to the input voltage. So that's why you will take a derivative with respect to the input voltage and not the output voltage anymore. So GM is del ID over del VGS, or derivative of ID with respect to VGS. And if you take the derivative, so that is represented here. So that's your del ID del VGS. And if you take the derivative of your ID equation, so remember ID is equal to half of K times VGS minus VT whole square. If you take a derivative of this with respect to VGS, what do you get? You have a squared term and you have this VGS with respect to which you're taking the derivative. So your derivative will become half of K times 2 times VGS minus VT. Correct? When you take the derivative of this equation with respect to VGS, you get this 2, which will basically this squared term will come to the left hand side, and this 2 and 2 will cancel. So you get K times VGS minus VT. So K times VGS minus VT, or K times V over drive, is your transconductance. Again, as you see that this is a very, very simple equation, that your transconductance becomes K times overdrive. That's it. And your current is half of K times overdrive squared. Okay. The transconductance can also be represented into multiple other ways. So one way to represent the transconductance is basically you can. So I can probably write it down here, that in that way it will be easier for you to understand. So I'll write GM equal to K times V over drive. Okay. Now you know that current is equal to half of K times V over drive squared. So if I take 2 times current and divide it by V over drive, that would still be K times V over drive, because 2 times current will be, this half will go away. This will be K times V over drive squared, and if I divide it by V over drive, I'll get K times V over drive. So GM is equal to K times V over drive, which is also equal to twice ID divided by V over drive. So twice ID divided by V over drive is also equal to your GM. There is another form of GM, which is square root of twice K times ID. And why that is true, see, your ID is equal to half of K times V over drive squared. Okay, just multiply ID with 2 times K. So your 2 and half will cancel, K will become K squared, and you already have V over drive squared. So you take a square root of K squared V over drive squared, that becomes K times V over drive. So these are 3 different forms of GM, and you can use any of these forms. So we'll show how to solve some of the homework 4 problems on Monday's class. But for that, remember that we can use any of these forms for your GM. It could be K times V over drive, it could be twice ID over V over drive, or it could be square root of 2 times K times ID. So all 3 of these equations are correct in terms of when you're trying to find out GM. It depends on which is given. If in the problem your V over drive is given and K is given, of course, you can find GM as K times V over drive. If current is given and V over drive is given, but K is not given, you can find GM as twice ID divided by V over drive. If K is given and current is given, but overdrive is not given, then you can find out GM as square root of twice K times ID. So all 3 of these equations are correct, and we'll see how to solve the homework 4 problems with these equations in Monday's class. Just go over some of, I think there's only 2 pages remaining here. Just go over them to understand how we are getting this amplification and separate AC and DC amplifications in this case. All right.